In this video, I want to go through some of the best practices that you can create indexes with so that you can gain the best performance for your queries. I'm going to execute 4 different queries on this beautiful table that I have here. I have a table with 3 integers, A, B, and C, and I'm going to play with the indexes on A and B. So I'm going to create a configuration where I have an index on both A and B. I'm going to create a configuration where I have a composite index on A and B, and I'm going to create a different kind of configuration where I have a composite index and a normal index on B. All right, and I'm going to execute the following queries where I'm going to query only on A, and I'm going to query only on B, and I'm going to query A and B and query on A or B, because that's most of the stuff that we do on the back end. We query with these particular filters. I understand we have end statements, we have other kind of aggregates, but we'll take it step by step. I hope you learned something useful with this video. With that said, let's just jump into this and play with this thing. All right, guys. So let's start with creating an index on A and another index on B. So I'm going to create an index on test A. By the way, I think I have around 12 million rows in this table. Not much, but enough for us to experiment with. So I'm going to create another index on B. All right, all done. Let's test. So we have an index on A and an index on B. So let's check our queries. So the first query I want to do is select C from test where A is equal 70. And I'm going to prefix this with explain and analyze. That will tell us how much the analyze took and the plan that has been used in order to do this thing. How about you jump into it? Do it. Fast. Fasto this. Very fasto. All right, so what happened? Obviously, the Postgres decided to use the index. However, it created a bitmap in order to query this index because there are a lot of rows. Look at how many rows. We have 9,000 rows. So it has to create a bitmap. Why? Because we have to jump back to the heap to pull C. C is not in the index. C is not included in the index. So we have to jump back to the heap to pull the value of C, right? After locating that. So we are building a map of all the values, the row, the tuples, in order to jump back to the table and pull that. And that explains why we have a bitmap index scanning the index itself that we just created on A. And then we jump back to the heap to actually pull those rows. And we have a cost, took 253 milliseconds, not that bad. All right, so that's what we have done. And what I want to do here, I'm show you that we can easily change this, kind of infer the decision of Postgres by actually limiting the number of queries. So if I say, okay, give me only 2 queries back, 2 rows back, look what Postgres decided to do. Because we have only 2 rows came back, Postgres doesn't need to take the overhead to build a bitmap, because building a bitmap takes a little bit of time, right? You have to compile this structure, you have to come up with all values, but it says, oh, I only found 2 rows, I don't need to build a bitmap. So I decided to do an index scan, a clean index scan, especially that these rows are contiguous, they are ordered, they are sorted. So the values that I'm gonna get, I don't need a map for this. I just can go pull those values directly from the heap. All right. So we use the index. How about to go to the other query? My other query is B is equal 100. So still pulling C, where B is equal 100. Let's take a look. So it took 250 milliseconds. We also use the index. This time we use the B index because, yeah, I'm querying on B. Naturally, I'm going to use the index on B. And then I hit the table directly with a heap scan using the values that I picked up from B. All right. Usually this is also a bad idea, right? Because you're not going to pull 10,000 rows. What are you going to do with 10,000 rows? And unless you're doing some sort of aggregate, that's a different story. But all right. So we have the value. So we're using the index. All right. So let's do this, the query now, but we're going to query on both A and B. So I'm going to do A equal, 100 and B is equal 200. Let's see what Postgres decides. So now we're going to do an AND between those squares. So Postgres decides, says, okay, in parallel, I'm going to scan the A index, I'm going to scan the B index because you gave me two values, right? And scanning those two values, I'm going to scan them and I'm going to build a bitmap, right? And literally you get a bitmap and then literally just AND those bitmaps. You're going to end up with a certain values, right? Some values will zero up, some values won't. And then you're going to end up with a set of tuples that you're going to hit the heap and pull the table directly. And that's extremely fast, right? As you can see, it's just happened is like how many values did you really return, right? We returned 6 rows. That's why it's pretty fast. And the ANDing operation is extremely fast as well. So that's what Postgres do in case of an AND. Let's try an OR. What would an OR do? I'm just going to change this to an OR. Boo! With an OR, it took obviously longer, and that explains a lot, obviously, because OR always brings more rows than AND, right? And now we did exactly the same. We scanned this index, we scanned this index, we brought the bitmap, we ORed them, got a lot more rows than we wanted, and then we got back the results. So pay attention to what this really happened, right? We're doing double the work. We're doing scanning this index, scanning index, and going to the table, giving it those rows, and then going to the table to pull these rows. All right. So now I'm gonna drop these suckers and I create a composite index instead. Let's do that. Test A, IDX, test B. All right, both the indexes dropped. Now what I'm gonna do is create a index on test AB. So this is a composite index, a little bit different, right? So we have one index that have both values. So it's going to take longer to create, and it's going to be more efficient for queries that have both A and B, especially the AND cases, right? Because the AND cases, we did a lot of work. And guys, don't pay attention to the values that how long it took, because this is really depends on the machine, depends on so many things. I want you to pay attention to how much work Postgres do, and that's what I'm explaining essentially. All right, let's do the first query on this. So now I'm gonna only query against A, and let's see what we're gonna do. Look at that. Actually, Postgres decided to use the AB index despite me querying on A. Why? Because A was on the left-hand side when I created that, and that matters. Because it's on the left-hand side, the values can be easily scanned. That's the Postgres rule. You can scan the values from the left, but you cannot scan them from right. Just the index are built left to right, right? And when you build that query, the index decided to use, the Postgres decided to use the index and then jump back to the heap, right? So it took 250 milliseconds to find all those values, right? And I believe if I do a limit, let's say limit 10, as you can see, it's an index scan instead of a bitmap. So it's like a little bit faster. All right, let's do the B. What do Postgres do when I do a B? 100. Ooh, you felt that, huh? It's a parallel sequence scan. Why? Postgres will not use the index. Why? Because you cannot use this composite index when you're scanning a filter that is not the left-hand side. It's either A and B or A. You cannot use B. So be very careful. So if you have a composite index on A and B, querying on B will not use the index. So what the table does, what Postgres does is just jump directly to the table and does a full table scan, and using multiple worker threads to do that, right? So it's obviously very, very slow. So very careful. Be very careful for that. All right. What happens if I do A and B? A equals 70 and B equal 80, whatever values. Look how fast this thing is. 0.5, half a millisecond. This is absolutely insane. That is the best case scenario. If you really all the time, if your queries are all the time like this, have a value and value, it's a great to create an index, composite index. If your application only does that, and hopefully only does that, and you're also your query in A, best case scenario is to create a composite index. Yeah, it's more costly to create a composite index compared to a single index because it stores more values, obviously, right? But the performance is remarkable, right? All right, how about OR? How about OR this? OR this ka? Oh, nope. Or in OR, all bets are off. You cannot use any of the indexes, right? I mean, Postgres decided in this case it's useless for me to query and try to use that because, like, you know what, might be faster for me just to go and jump to the table scan, do a full table scan instead. So that's what Postgres did, and Postgres does. Most databases do all these decisions on behalf of us, right? So, okay, maybe it's better to do this versus do this. I mean, if you look at this, it's like, okay, you have an index on A, you can query on A. I mean, you have an index on A and B, but you can query, you can use the index for A. But Postgres decided, no, you know what? It's way slower. I'm going to do this. I'm going to do a bitmap and then go for B. I don't have an index. So anyway, I have to go jump there and do the full scan anyway, right? What happened if I do a limit? Limit 1, sequential scan on this. It's not even parallel, it's just sequential because we know we're going to pull only first row. That's fast, and that's directly on the heap. All right, guys, the final thing we want to do is we know that B suffered. Queries on B suffered when I have a composite index. So what I'm going to do here is show you that I have a composite index on A and B. What I'm going to do is create an index on test B in addition to this index, and then execute the same queries again and see how things are doing. All right, so what will happen now if I query on A? We saw this because we're going to use the composite index. That's fine, that's fast, right? That's nice, right? How about if I use B? If I use B now, we're going to use your beautiful index that you just created for us. So that's kind of a compromise as a backend engineer, as your database engineer. You're going to say, okay, some queries, I'm going to use the B to query this. So I might need an index there, right? So you're going to create an index in this case to speed up these queries, right? And then obviously we're going to hit the table and the heap in order to do that. All right. Let's do A and B. A and B. Absolutely genius and fast. Look at this. Right? We're going to use the composite index because of the B, right? Right? How about A or B? Or now that we have an index on B and an index on AB, now Postgres is, oh, wait a second. Actually, we have an index on B. I can query the index on B, build a bitmap, and then I can query. Since we're querying on A, I can still use the composite index because it's a left-hand side. I can use the query and the index on that, build my bitmap, beautiful bitmap, build a single bitmap, jump to the heap, and then pull the rows that I want. All right, guys, that was some of the best practices that you can do to work with indexes, right? This is just some of them, right, guys? Sometimes indexes can shoot you in the foot. Sometimes they are great, but just learn how to use them. I can't possibly in 10 minutes explain all possible combinations, but hopefully this helps you kind of understand what the database is doing when you are actually querying the indexes. This is very, very critical as a backend engineer. This is one of the skill set that you have to put in your belt when you're building database applications, essentially. Hope you enjoyed this video. Give it a like if you like it. Give it a dislike if you don't like it. I'm going to see you in the next one. You guys stay awesome. Goodbye. In this video, we'll look through how the database optimizer decides which index to use, especially if there are multiple indexes. This is very useful if you want to know whether your table needs an extra index or not. Because if you have multiple indexes, how do you know which index the database is going to use? It's not going to use all of them all the time. It really depends. This video is going to explain these kind of cases, right? This video is not going to discuss the combined indexes, one index that have multiple columns, right? Because I already discussed that. So let's say we have a beautiful table with just 2 columns, F1, F2. column 1 has an index, F1 IDX, and column 2 has an index, F2 IDX. And we're going to do a select star from the table where F1 equal 1 and F2 equal 4. So let's go through some scenarios to see how the database optimizer decide to, hey, should I use F1 index or F2 index? There are so many ways to solve this, to look for these values, right? So let's take a little case number 1. Case number 1 is when the database optimizer decide to use both of them. So what it does, it queries F1 IDX looking for the value 1 in this case, finding all the row IDs that matches and tuples in case of Postgres, row IDs in case of Oracle and SQL Server, and it collects all these row IDs. And then it does the same exact search but with the value 4 on F2 IDX. So it searches and collects a different set of row IDs, and in case of an AND, it will essentially do an intersection. It's like, okay, what is the values that are in here, not in here, and then essentially merges the results. And or it's gonna merge the result and essentially union them, right? So that's how it does it. The effective result set, the row IDs are collected. That's the final result. You go to the table if necessary, obviously, and you collect the actual values from the table, from the heap, right? So when does it actually do this? It really depends. If the values are not too small, if we know that we're not going to get so little of a result, because if we're going to get a little of a result, it's not worth searching both indexes. One is enough, right? Especially in case of an AND, right? These cases gets really tedious, right? And if we get too large of a result, if we know that the index is going to return so many rows, so many row IDs, it's just not worth looking through the index. In this case, we're going to go through the table index scan, right? So it really depends on, and that's all heuristics the database uses to decide what of this, right? So that's case 1. So let's talk about case 2. The case 2 is when the optimizer decides to use one index over the other. So let's take an example. We're going to show an example right here. The database decides to use F1 index only, search all the rows for the value of 1, and then we collect all the rows and then don't use the second index, right? Let's just go immediately to the table, fetch those rows, and then do a recondition, refilter the results based on F2 equal 4, right? So databases usually do that when they know that F2 index returns so many rows while F1 returns very few rows and the condition is an AND. Because if I know it's an AND, then I know, of course, I'm going to go with the smaller one, because anything that doesn't match F1, right, is out of the result set, right? So it's going to go with F1. Example is a primary key. If I have a primary key, the database almost always going to use the primary key index. In case of an AND, again, with an OR, it's a different situation, right? It's because you get more results, right? And then go back to the table directly and fetch the results we want to, right? It's just not worth searching two indexes, because B trees are not cheap, guys. And even LSM trees are not cheap. Indexes are not cheap to search. Yeah, if you're searching, if you know that you're going to get so few of the values, then it's worth searching the index. If you know that you're going to get a lot of rows back, then it's not worth searching the index, and maybe table scan is actually better. And you might say, how do you know? How does the database know that, hey, this index is going to result so many rows versus this search is going to result into fewer rows? Well, there's something called the statistics. The stats, really powerful. The database keeps stats of the table, says, okay, here's the table, here's approximately how many rows there, here's approximately how many ones are there, here's approximately how many threes are there, and all these kind of values. So they are not 100% correct, but they give really a lot of values. And you can also always update these statistics with a command called analyze, or sometimes called, I think, gather statistics in Oracle. Right? So that's the idea, okay? It really, again, depends on an AND or an OR here. But here's one example where we use one index over the other, right? Just one and then filter. So an index with a filter, that's case 2. And case number 3 is just the database decides, you know what? You guys suck. Both indexes suck. I'm not gonna... The search to get for the value F1 equal 1 and F2 equal 4 it's just going to return the whole table, almost the whole table, 3/4 of the table. I did my math, and this is what I think. So guess what? I'm not going to use both of you. I'm going to already go to the index because I need to go there anyway, because I'm going to select other columns. The database decides to search. The search will lead so many rows, just like let's go to the table directly and do filter because it's much cheaper. And some databases like Postgres does a threading, multi-threading, and issues so many workers, so you can do multiple workers to scan the table, right? So table statistics are very, very critical here. So if you got some wrong result, right? Let's say here's where things get nasty. Sometimes I got bit so many times with this. Here's an example. You bring a table, very fresh table, right? Empty, right? So there is statistics almost 0. It knows that, hey, table's empty. You insert 1 row, you insert 2 rows, 3 rows, and then the tables get updated every asynchronously, right? Now it knows it has only 3 rows. And then you do an operation to insert 3 million rows or 300 million rows. You just in bulk. And you're just immediately after you inserted, you just do queries. You know what will happen in this case? The database, if you don't update the statistics, you'll execute something like this and will say, hey, what should I do? Let's look at the statistic. Oh, this table has only 3 rows, so it's always easier to scan it fully. And in this case, it's going to do a full table scan, pulling all the 300 million rows to look through this. I've got bitten so many times by this because I forgot to update this, or immediately I did my queries after this. So always, if you're using Postgres, do analyze. What's the other command? Vacuum, full vacuum to clean up all that garbage, and then after that, just do an analyze. In Oracle, use gather schema statistics. In SQL Server, I forgot what's the correct execute planner. I forgot what it's called for the SQL Server. But yeah, you can do all these kind of stuff, guys, essentially. And for those who want to advance stuff, if you know what you're doing, if you really know what you're doing, you can use database hinting. You can, in the query, include some sort of a comments like this one, the one you're seeing on this screen, to kind of force the database to say, hey, you database, you're dumb. You don't know anything. Please trust me. I want you to always use the index of F1 or use the index of F2 because I have more knowledge than you do because of certain situation, right? Because my application, I know what I just did. You are not caught up to what I just did as a database. So trust me, your stats are not up to date to what I'm about to do. Plus, maybe the human in this case are way smarter than machines, right? Unless the AI picks up anytime soon. I don't know. I don't think it will. But anytime soon, so it's gonna take time. All right, guys, that's it for me today. Very quick video talking about how these databases use the indexing. Very, very critical. Again, I omitted so many details, for example. So we'll give this we'll open up for questions, and we'll have some discussions on what if there is an or if there is a join. It completely changed the dynamic, right? The building a database is not something easy. It's really, really difficult. But these tools will help you while you're executing a query. At least you know, hey, I know that F1 is not going to have a lot of values. It's going to have, let's say, it's going to have a lot of values. Let's say you have 1, 2, 3. That's only the unique values you're going to have, right? Or, I don't know, let's take a real example. Let's say you're building a customer database, right? And you have the states, right? In the United States, like California, Texas, whatever, all of them, right? And let's say your database is almost exclusively all people from California, right? And you have an index on the state field. Obviously, if all of them are California, that's just a useless index right there. Because like, what is gonna give me is if I search where state is equal to California, that's the entire table, right? So, but let's say you have 3 customers on Texas and 1 from Florida. Searching that Florida, is way faster than searching the 300 million, no, 300 million, that's the entire United States. But you get the idea, right? If you have one value or few values, indexes are beautiful for this, right? But if you have so much rows that you're coming back, that's where you play the game of multiple indexes. Okay, you know what? I know that this row, this index is going to give me this much rows back. I'm going to slash it down with another index. So let's put that. But you have to think of how sparse your table looks like, right? And in these kind of cases. All right, I'm going to leave you there, guys. I'm going to see you in the next one. You guys stay awesome. Goodbye. Creating an index on a production database, especially on the large table, can take a long time. And not only that, but it also blocks edits on your tables. So you cannot really write. Writes are blocked when you want to perform these kind of operations. So which kind of sucked, right? You can do reads just fine, right? For example, select from grades where ID is less than 10. That works. You can read, but you cannot really write because the index is using that field, that particular field, to build the index, right? So that kind of sucks. So Postgres came up with a better approach to create index called create index concurrently. And this is what I'm going to show in this video. Go ahead and drop this index and do the concept of creating the index concurrently so we can allow write and read while the index is being created, which is very, very valuable, right? You cannot afford going down or pausing or locking transactions when you're essentially creating an index on the production environment. So we're going to do the same thing, create index G on grades on the field G, but we're going to add a word concurrently. What that will do is it will do multiple scans to perform them, and it will wait for all the transactions, the write transactions, to finish before it actually, and it will pause itself, right, while there are write transactions. So now, if I want to insert into grades, right, values 1, for example, I can do that. Can I read? Definitely, you can read. Where ID is less than, that's totally fine. You can commit and you can read, right? However, what this will do, because of the multiple scans, because of the waiting, right? This operation is going to take way, way, way longer, obviously, it's going to consume more CPU, obviously, and it's going to consume more memory. So it might take some of the precious CPU memory from other processes. However, not only that, it can also potentially fail, guys, right? Because consider if this index is essentially a unique index and you're inserting duplicate values where the index didn't exist, technically the index will end up in an invalid state. And at that point, you have to drop and recreate the index. So this was create index concurrently. Very, very useful tool. And I heard that Postgres is going to make this the default, right? Because when you create an index, you don't really care if it takes a long time, right? You really care about your actual production live database writes and reads be fast, right? And unblocked, while in this case, you want your index to be created, and it's okay if it takes a little bit long. So this was a very quick video talking about this new feature. Guys, I'm gonna see you on the next one. Stay awesome. Goodbye. Bloom filters are one of those concepts that always confused me for the longest time in computer science. I'm gonna take a few minutes to actually explain it to you guys, and not what are they, but why do they exist? So I'm gonna flip the question a little bit. If you're interested, stay tuned. So here is a problem. Forget about Bloom filters. Here's a problem today that we know how to solve, but we can do it better. I'm gonna write a service, a web service, Express, Node.js, right? That essentially check if my username exists or not. And if you think about it a little bit, this capability, this feature is very simple to build, right? Build a database with all the usernames. As you start writing usernames, if you want to build this interface, you make a GET request. Does Paul exist? You make a GET request to the server, Express, Django, anything, and then you execute a query against your database, select username from this table. Hopefully you have an index there. And if the record comes back, that means the username exists. If not, then it doesn't exist, right? Problem with this is very slow, right? And this feature is gonna be very popular, right? All these users going to this web page and typing, hey, does test 123 exist? Does whatever, right? Everybody wants a fancy nickname, right? So here's the problem, right? This is very slow. So what do? Well, I heard about this Redis thing, right? That is actually in memory database. So let's take it from disk and put it in Redis. Well, that's fine. We're gonna do the same thing, execute the same GET request, but this time I'm gonna hit the database, right? And if it's not there, okay, I might sometimes need to go to the actual database because these two can get out of sync. So you created some inefficiency and you actually doubled your memory footprint because you're storing data here and storing data here just to solve this simple problem, okay? So we know how to solve this thing, but some smart people, computer science professors, came up with a solution, very efficient solution, and they called it Bloom filters. So let's explain what these things are. Okay, so with Bloom filter, we're gonna use some in-memory representation. Usually it's very tiny. I'm using 64-bit in this case, okay? And this 64-bit magically have some numbers, right? In this case, the bit 0 is not set, so it's 0. This is 1, this is 0, 0, 0, 0, and this is 1, right? So how does it come up? We'll come to that. But here's the thing. If we're gonna make a request, hey, does poll exist? We will make a request to the server, and in the server we'll write a function. We will hash the string poll and mod it 64. And if you know mod, what will happen is this result will only come back with the result from 0 to 63, right? And just like the out of the box, you're gonna get collision all the time, but that's fine. So in this case, poll is bit number 3, right? And if we go ahead and check in my integer, in my 64-bit integer, this is the filter that we built. Does this bit exist? Is it set? No. If it's not set, then you can absolutely, with 100% guarantee, say that poll does not exist in the database because it's not set here. And we're gonna show how that happened. Okay, so poll doesn't exist. So I didn't have to even query the database. Let's take another example, right? Where I'm gonna check if Jack exists. I'm gonna make a GET request to the server and I'm gonna mod the string Jack. First of all, we're gonna hash the string Jack, get a bunch of big number, right? And then mod 64, I'm gonna get a value from 0 and 63. It happened to be 63. I check the bit of 63. Oh, it's set. And if it's set, here's the thing. If that bit is set, that means Jack may be there. And why is maybe? Maybe because there might be another string that matched hash and mod 64 that resulted in 63 and was set. Not necessarily Jack himself, right? But some other string that matched it. But that is actually enough for us. If it's set, then, oh well, it's set. I'm gonna take the hit and hit the database. So I kind of saved myself some queries at the database. Is this perfect? No, but it's a very efficient thing to actually query, right? To prevent unnecessary querying. By the way, Cassandra uses this in their implementation of consistent hashing all the time, right? The SS tables and all that stuff. They use this internally, right? Because anytime you want to avoid an expensive query to check if something exists or not, or if you want to do this query but you're not sure if you're gonna get a result or not, Bloom filters are very useful. There are some disadvantages to this, but let's look at actually how to create a Bloom filter. I have a brand spanking new bit set here, 64-bit, right? And I'm gonna create user Jack for the first time. It's a blank database, right? There is nothing in it. I'm gonna create Jack. So if I'm gonna create Jack, I am going obviously to make a post request to the server, to the Express server, and I'm gonna hash Jack mod64. I am going to get 63 in this case. And what you do before writing to the database, the username Jack, is you set this bit. Niceties, isn't it? And then you obviously write it to the database. So see, this is how we start building this in-memory representation of Bloom filter, right? And then let's try Paul. Hey, I'm gonna create a user Paul. Poof, post Paul, right? Mod 64. What do we get? Oh, bit 3. Let's set bit number 3. All right, so far it's good. Let's try, and obviously we write it to the database. Let's try some other user, Tim. Well, I'm gonna take Tim and hash it mod 64. Guess what? I got number 63 again, and that's absolutely perfect. That's okay, because you only have 64 bits. Obviously, all the strings and names in the word, you will fill between these things, right? And obviously, when you say 63, it's already set, so you don't have to even bother yourself setting it because it's already set. But you always have to head the database and write it, all right? So that's how it's actually made. Let's take another user, Ali, all right? So Ali, hash Ali and get mod 64. You're gonna get bit number 4 in this case, and you're gonna set that bit, all right? And then obviously write the database. All right, guys, so that's essentially Bloom filter in a nutshell. I know the actual implementation of Bloom filters are a little bit fancier. They use like 3 locations and all that stuff, right? Sometimes they have more bits, right? They use 3 hash functions just to make the odds harder to get, right? And that's just, to me, that's just an implementation. But if you understand how it works, that's how it works, and that's why it exists, right? So some limitation of Bloom filter, you can get into a case where all of these puppies become 1 1 1 1 1 1 1, and in this case, your Bloom filter is essentially useless. You became the first case where you're always gonna hit the database. It's not really harmful. It's not gonna slow you down, but it's not gonna give you any benefit per se, right? So you're gonna have to think about this. Like, the bigger you make this thing, right, then you kind of interfere with your memory footprint. But I mean, it depends how big it is, right? Really. But the shorter it is, then you're gonna get all these false positive cases where you're gonna always hit the database regardless, right? All right, guys, that's it for me today. Hope you enjoyed this video. Gonna see you in the next one. You guys stay awesome. What's going on, guys? My name is Hussein, and in this video I want to discuss the idea of working with billion row tables in general. And this is a very, very interesting point, because as you design a system, it will force you to ask a question. Your table design, your document design, whatever flavor of a database you use, how do you anticipate these tables to grow in the future? After 1, 3, 4 years, do you anticipate these tables to grow so large that they're gonna reach the billion level? So in this video, I want to kind of discuss how do we work with such huge volume of data, right? Because there are many ways of tackling this problem, and I want to just discuss some of them. I have 3 concepts here to discuss. Obviously, guys, if I missed anything, let me know in the comment section below. Before we jump into the video, guys, this video was basically inspired from my comment section, specifically with Vinny. He's a great database engineer, and he always finds mistakes and things that I say wrong, and obviously has great feedback in general on my videos. So I like this is just a shout out for him. So it was spawned as a discussion on my Twitter system design video when I came up with this arbitrary design for the fellow feature, which I'm gonna reference the video right here. Go check it out. And so as a result, that design generated a table which is very, very huge, right? So what I basically did is I have this following feature, right? So I have this person following this person. So I put the whole thing in one table and added 2 rows with their IDs. So this person following this table. And I said in the video, this is going to be a huge table. So what do? We had a discussion back and forth of what do we do with these kind of situation, which inspired me to actually make a video to discuss what do we do? What do people do today if you have a large table? How about we discuss it? So I have 3 basically concepts. The first one is brute forcing your way to process the table or work with the table. So if you're trying to find a row inside this table, right? What you can do without the concept of indexing, without the concept of anything, brute force your way, which is do multi-threading, do multi-processing, and chunk the table into multiple segments and search in parallel, right? That's how basically big data essentially and concurrent Hadoop works, right? So it's like map and reduce the subset of the table into smaller concepts so you can run in parallel and brute force your way and find what you're looking for, and try to do the process yourself, right? So that's the idea. Can I break this table into hundreds of pieces and search these spaces in parallel concurrently, throwing this problem on 100 machine cluster? That will work sometimes. That's why I want to discuss the second point, which is, can I avoid processing the entire table? Can I avoid processing the entire table and instead process subset of this table only? How do I do that? The best approach is use indexing, right? Because that's what we do. If we index a column on a table, then you essentially create a structure on the disk that will basically, it's a B tree or LSM tree that will help you reduce the subset on what you're searching. So instead of searching the entire table for what you want, right, you search only a small subset, which is the index, and that even it's a scan to find what you want, and then you, by finding that, you kind of narrow what you were looking for. It's like a binder in the secretary's office, right? Where you have, okay, there is the book and there is the letter A, and any contract that starts with A is this. Any contract that starts with B is this. Any contract that starts with C is this. So you see it in color coded, right? So if your contract is, I don't know, company is called Zebra, so you only immediately go to the Z color and then you start searching, right? So you minimize what you're searching for. However, that's indexing. So let's search with a smaller set, right? So instead of having the whole table, let's reduce the set, right? So instead of working with 1 billion rows, maybe we're working with few millions in this case, right? Can I even go and reduce that set even more? That's where database people do tricks like partitioning. So partitioning is on disk by this huge table is now broken into, and I'm talking about here essentially horizontal partitioning, not vertical partitioning, right? So horizontal partitioning means like slice the table in half, almost like in the middle, and then you say, okay, rows from this to this is on this location on disk, right? And then rows from this range to this range and in this location. It's different than indexing. So the whole thing is still indexed, but we're literally partitioning in, the table into multiple parts. So now, how do I know which partition to search for? You need another concept that tells you which partition to hit. And if you're lucky, you might search one partition only or couple. And this is called the partition key. So you always partition on a key. Very similar to indexing, except the indexing works on the whole table. Partitioning works also on the whole table, but it will partitioning will break down the table into smaller and smaller pieces, and now you will have different indexes per partition. Usually the database take care of all that stuff for you, so it's almost transparent. Working with indexes was working with partition is transparent from you as a client who queries this table. So it's incredibly fast, right? So if you know where to search for, you can hit the right partition and only hoping that the partition that you're searching for is in that. And indexing also make that even smaller set. So that's pretty cool, right? And that's still so we have one database still. We have one machine, and we broken this into multiple partitions, and now I can search exactly what I want to. Now you can distribute that even further across multiple hosts by doing sharding, right? So similarly to the concept of partition, you can still have partitioning and also add the idea of sharding on top of that, which adds a little bit of complexity to your system. But now you put the first 100,000 customers in one database, and you put the second 100,000 in one database, and they don't talk to each other. And here's now the problem of transactions, right? Because they are two different databases. You just reduce the size of the table, obviously, but now you complicated the client, because the client is now should be aware of the shards. Like, okay, I am searching for customer number 500. Which shard should I hit? Oh, you hit shard 1 because that's where it is, right? And now going down deep into that shard, there are partitions of that table, and going down into each partition, there are indexes, right? Or index. And now you basically narrowed the billion row into maybe few thousand or few 100,000 rows, which is pretty good. So that's the idea of what we do, right? Shard, partition, and then index, and then find a row exactly what we're looking for. So that's the idea of limiting what we want to work with. And the final thing is, as I started thinking about it, it's like, okay, maybe we can avoid all this together. Why do you have a billion row table to begin with? So that's on the database designer, which was me in that case, right? It's like, okay, maybe it's not a good idea to have a table so large. Can we solve this problem so that I don't need to have a billion row table? And in case of the Twitter following example, we might actually be able to. I still didn't complete the thought yet, but if you have like a profile table, okay, this is my ID, this is my name, this is my picture, we can add a field called followers count. It's an integer. We'll come to that. And now there is another field. Now most relational databases support JSON. We can put a JSON there, or a list field, and add your followers in your profile. So now we don't have a relational table that tells you, oh, this guy is following this guy is following this gal. Nah, we have one profile, and if you want to get your followers, then you go to your profile and fetch the row and pull that information, and that's, you have all the profile. And every time someone follows you or you follow someone, now the hit is on the right level. If I want to write, hey, someone just followed me, I need to update those two columns. I need to update the count, and I need to do that. I didn't have this problem in the first design, but the first design wouldn't scale as better as this, in my opinion, right? You can, now we start worrying about the right throughput, but I don't want to go through that stuff, right? We can do message queues where we can, okay, let's write it asynchronously, update that. Yeah, there will be a little bit delay. Who cares? It's a follower count anyway. We're gonna pick the queue and then slowly just update these things. So we have many ways to solve a problem. So to summarize the whole video, instead of working with the whole billion table row, try first concurrently processing it. Maybe I'll flip that a little bit. Maybe try to avoid having a billion row. That's the first thing. I kind of said it last, right? The second one, if you can't avoid it, then can you index it? Obviously, what field to index them? Can you partition it, right, on the same table, on the same disk, right? Can you partition your tables so that they are smaller sizes? And if you can partition and you can index, can you even, do you really need to shard it so that if it's even smaller and smaller pieces on multiple hosts, right? Because if that host dies, then that's a problem, right? So you even partition it on horizontally, essentially, on multiple databases, right? Shards. That will create complexity, which I try to avoid. I talked about that a little bit. And then finally, if you can't do any of that stuff, just do MapReduce, just run parallel processing and try to run your work so that you process the billion row concurrently with a massive army of machines, if possible. If your database is transactional, then that's kind of pointless, because the moment you start the army searching or working with your huge table partitioned, right, spliced, then it will go out of date the moment you start, because people are start editing, right? People changing all the time. All right, guys, I'm gonna see you in the next one. You guys stay awesome. Goodbye.